Now let's look at how we can convert our previous expressions in quantum mechanics to path integrals for fields. Now let's remember some critical objects we use in obtaining the path integral in quantum mechanics. One thing, we had the position operator. We looked at the eigenstates of that position operator. And then we use the resolution of identity in terms of position kets. This integral from minus infinity to infinity was 1. Now, if you remember our first lecture on how we switched from the quantum mechanics to fields, we said that we have at every point, here x is actually some quantum number describing the properties of the particle. We said that at every point we have such a property, or in our analogy we used that we had an oscillator at every point in space. So these were our states, which we also wrote as phi. We converted the x field into phi, and these fields, these new fields, they have a value at every point x. So this is how we switch from quantum mechanics to field theory. And of course we also converted this position operator to a field operator, such that when phi x of t is let's say just x is acting on this ket x, it would give us well, let me write it somewhere else. This gave us the number phi of x. Well, let's say x0. This is x0, phi of x. Keep in mind that this phi of x labeling the ket is mainly a collection of various quantum numbers at every point. And this field is the analog of the position operator at the point x0. So it just extracts the value of the position at the point x0. And well, this is analogous to what we had over here. This x operator acting on this ket gives us x of x. Now here we don't have a single x operator, we have a collection of them, and each one have their corresponding eigenvalue. So this resolution of identity will also be modified. Now we don't have single coordinate, we have a coordinate at essentially at every point. So the resolution of identity in this case will be phi of x, but now we have to integrate over all these values of phi of x at every point x. So this is our new resolution of identity. So using these definitions, we had the path integral expression x initial to x final e to power minus I h tf minus ti. This was written as well, we had two expressions, dx and dp, e to the power I integral pq px dot minus h dt, where dx was just the product of the measures of xn, and let me just write it tn. They are at different times, so the product is over tn, and similarly for the momentum. Well, here the analogous expression will be, now we have the final field configuration e to power minus I h tf minus ti, the initial field configuration. This will be equal to a measure over the fields, a measure over the corresponding momenta, e to power I phi of xt, pi of xt, the conjugate momentum, minus the Hamiltonian density of phi and pi, integrated over all space-time. These are the densities. And here the measures are again the product of the measures of the fields at various points and time. And the corresponding measure over the momenta. And in the quantum mechanical case, we also had this 2 pi. So we can also introduce the 2 pi over here. Now these normalizations will not be important for us, as we will see in our next video. And we also had another expression we could evaluate, especially if the Hamiltonian had a part that depends only on quadratically on p. We had a simpler expression, and in that expression, this matrix element was given as just a single integral over the trajectory of the particle, e to power I. This time it's just L x dot dt from Ti to Tf. Here this measure was up to some normalization, the product of the Tn. And here we can also do the same thing. So this matrix element phi f of x Tf minus Ti phi I of x will be written as a measure over the field configurations of e to the power I, this time the Lagrangian density d for x, the integral starting from time integral starting from Ti up to Tf, and the position integral is just overall space. And well, usually we will also take this Ti to be minus infinity, Tf to be plus infinity, but we will come to that later on. And furthermore, this measure is some normalization. As I said, this normalization will not be important for us. The product of the phi, the field at different points in time. And the conditions on these trajectories over here was, in the case of the quantum mechanical path integral, the x at Ti should be equal to xi, and x at Tf should be equal to xf. And similarly, in the field theory case, we have these when we are summing over all these possible field configurations, the restriction is that the field configuration at Ti is given by phi I of x, and the field configuration at the time Tf is given by phi f of x. So this way, this is just the analog of this expression over here, generalized to fields.